All right, so I'm Stranger on Solaris. How are you doing tonight, Austin? Sorry, I just want to do that. So tonight, I'm going to tell you about the shape of clouds, or as in my favorite sci-fi movie, Solaris, where characters were trying to understand amorphous materials they found on Solaris. I'm going to tell you a real-life story about how astronomers have tried to describe seemingly amorphous structures they found around star-forming regions. And by describing these structures, they have come up with a pretty good story of how these structures form, which in turn leads to the formation of stars. All right, so let's take a few steps back to what astronomy used to be before the 19th century. At that time, astronomy was largely focused on the study of point-like sources, and one of the most famous examples was probably Galileo's observation of Jupiter's moon. As shown here is his drawing. And one very important reason that Galileo can do this, build his cool telescope that Dr. Spectral Billionaire didn't mention, was that he worked for the enormously rich Medici's in Tuscany, Italy. And he actually named these moons Medicea Sidera, or Medicean stars, in the beginning. So it's all simple and easy for point-like sources. You observe them, you draw them on a piece of finer paper, and you present it to your Lord, and you get your money. So it's so easy, right? But what about more extended objects? They may or may not look like a dragon. So imagine Galileo today observes a nebula that looks like a dragon, and he's all very excited to present it to Lord Medici. So he observed it, he drew it on a piece of finer paper, and he show it to his Lord, and his Lord will probably go like, "What's this crap?" That would definitely happen to me. But unless you have something magical, and that's why I'm showing you the first photograph made with natural light in 1827. And this is actually the first photograph, and this is what it looks like today. And you can actually go see it at Harry Ransom Center at UT, which is pretty cool. Right, so only after the first half of the 19th century, the astronomers were able to record celestial objects as well as celestial events. As shown in these daguerreotypes, or one of the photographic plates in the early times. And then about 3/4 of a century after the first picture was taken, the first systematic observation of extended objects, as you can see here, was made by Edward Barnard. And he go about and took pictures of these extended objects. And then at the end of the day, he came up with a pretty good story. I think there are holes in the sky. There are actually, that's actually true. So in the beginning, he thought that there are actually voids of stars where there are simply less or fewer stars than anywhere else. And that, as we know today, as we learn today, if he really push it through, he might become a really good expert in dark matter. But it wasn't the case for these extended objects. In fact, these are more likely associated with what have been known as nebulae or nebulosities. It's just that the materials there is so dense that it dims or block out all the background starlight. All right, so 2 decades after the observation of nebulae on photographic plates, astronomers developed the techniques needed to collect the cosmic static. So cool. So what I'm showing here is actually the first radio emission map of our own galaxy, or the Milky Way. But later on, astronomers realized that the radio emission can be further broken down into a few components, and one a very important component shows up as these tiny little spikes on one of the first spectra. And these are actually emission at characteristic wavelengths that's associated with the internal motions of different species of molecules. So then astronomers have learned a little bit more about these nebulae. They are molecular instead of atomic, and astronomers call them clouds or clumps. So now you have better terms than dragons to describe these extended objects. So you can call them clouds and clumps. And of course, when you are a researcher, you always want to come up with cool new terms to include in in the title of your paper. And that's what Bart Bach did at around the same time. And he specifically said that he wanted to omit from consideration the wind-blown wisps and filaments, which you just saw on Barnard's photographic plates. And he looked specifically for circular or oval dark objects, and he called them globules, or in a more general sense, gas spheres. And that's what physicists in general do, because you want to describe the cow with a sphere, right? And that's what inspired the first few models in describing these extended objects. So if it's a sphere, it's easy because it's spherically symmetric, and you can actually describe the radial profiles of densities and other physical properties as well, and you can simulate them in your model. So now, besides clouds, clumps, filaments, we also have the globules. So now you would think that there's no nouns unturned in naming these extended objects. You can always make new one by combining the old ones. So after, in the 1970s, astronomers start to look into clumpy clouds and globular filaments. And there's actually one very good reason to why astronomers have become capable in the 60s and 70s to describe these kinds of objects. It's simply because the astronomical observations have had a larger dynamic range than before. So you can, at the same time, see a very long filaments, which is also more diffuse, as well as the very dense globular shapes inside the filaments. And that actually brings us to what later known as hierarchical structure formation. So for example, here, for this very long filament, the astronomers Schneider and Alpgreen actually broke it down into, well, actually, when you read the paper, you would think that the breaking down of the cloud is fairly arbitrary. But anyway, they proposed that the cloud is composed of 5 different groups of objects, so A, B, C, D, E, and within each group, there you can actually you can further break it down into 1, 2, 3, 1, 2, 3, 4, etc., etc. So what hierarchical means here is actually a constant law connecting the larger scale to a smaller scale. So whenever you find a large object, it's more likely that it breaks into smaller and smaller substructures instead of the entire structures collapsing and forming stars. And that brings us to the end of our structure formation story, which are the dense cores that we find at the densest part of essentially Barnard's nebulae. And after that, gravity will just take care of the rest and make stars form. But it's important to describe the structures, formations before the stars form. And by describing these objects, as you've seen now, that we have clouds at the largest scale, we have clumps at slightly in between them, we have globules and filaments and all of that, and at the very center of them, we find dense cores, which will in turn form stars. And the astronomers describe this process as self-similar. meaning that whenever you observe something, you would always find similar structures at a smaller scale. And one very good example of this on Earth is the cloud itself. And if you meaning that if you take a picture of the cloud and by zooming in further and further on, you wouldn't be able to tell whether or not you're at a certain spatial scale. A more professional term to describe this process is stochastic, and it's defined as that the entire thing can be statistically described or analyzed, but you cannot precisely predict how the cloud itself may look like. So this is actually very important because that requires astronomers to go around and observe as many clouds as possible and to analyze them in a statistical way instead of just by as you do to other like planets when you can actually look into the composition of one single planet. All right, so what's so important about the early days when people were trying to describe these extended objects with funny terms, with clouds, clumps, filaments, wisps? It actually turns out to be true. So most of the story that was developed before the 1980s can now be proven true with new observations. For example, here I'm showing two observations from Spitzer, and Myers et al. Actually proposed that most of the star-forming regions are found in these kind of hop filament systems, basically at the convergent points between several filaments. And then with better observations, we can now, instead of saying, hey, I find many cores in one very long filament, you can quantitatively describe that many of the star-forming cores are found within the densest filaments that we can now see with high-resolution observations. And then hierarchical formation has been quantitatively proven true as well. If you go look at not just the two spatial axes on the plane of the sky, but also the velocity axis, which you can get from radial observations, if you find connecting points, then eventually you are going to identify even finer elongated structures within filaments that sometimes people still give them funny names because that's how you get citations. And so people call them bundles or fibers. But here it's essentially telling you that there are even finer structures within the filaments that people have been talking about before the 1980s. And then within them, you further find core-like structures that gives you stars. So now, with the new observations and new numerical algorithms, you can actually say that hierarchical structure formation is true. And you can quantitatively say how true it is. And then there are other algorithms being developed. For example, dendrogram, which is essentially a tree diagram that will tell you about what the hierarchy in this kind of observations of nearby molecular clouds look like. And furthermore, we can now simulate it. So instead of a cloud that turns into stars, you have intermediate steps that you can take in simulations by putting in different physics and make the cloud to look more like filaments, and within those filaments you can find the cores as you do in observations. And then last but not least, besides the many types of physics that you can put into simulations, you can actually use various kind of numerical algorithms to analyze what algorithms might be more sensitive to one physics than the others. So all this is actually made possible by not only the development in observations, but also the data science, which is a hot word now, And yes, and astronomers have come to be able to prove that what people talks about in the 1980s were true. So I would like to end by quoting my favorite movie director, Tarkovsky. I can only say that the image stretches out into the infinity and leads to the absolute. And even what is known as the image, many-dimensional and with many meanings, cannot be put into words. But it turns out that putting them into words really helps us to understand these structures. And let's take a look at 3 esteemed professors from 3 famous institutes analyzing an analog model of the Orion molecular cloud, what you're seeing here. This is the most fun conference I went to because the entire seminar of about 40 people actually put into efforts of building the Orion cloud there, and I actually built those tiny outflows. And it's actually helpful for us to understand the 3D structures of this giant molecular cloud. And I would like to say that the next time when your friend tells you that he saw a dragon in clouds, believe him. All right, thanks.
Thank you, Stranger on Solaris. Anyone from the top? Yes.
The filaments, were they comparable to the pillars of creation?
To what?
Pillars of creation, star forming.
Yes. So actually, you
Repeat the question,
will.
please.
Okay. So the question was that are the filaments that I talk about comparable to the pillars that you actually find in many of the dark nebulae that you can see in your own telescopes? And the answer is yes. So it turns out that these kind of elongated structures are everywhere in the everyday nebulae you see through your own telescopes. And there are actually many questions to be answered regarding them. So, yeah, or you can continue with whatever. Okay, yeah.
Good question. Anyone else?
So the question is that what's the chemical composition of these nebulae and different structures in molecular clouds? And the answer is, if you remember from the previous talk, a lot of them is CO. And of course, molecular hydrogen as well, because these are really the densest regions that you can find in our own local galaxy, where you would expect that in the future, these are the star factory, right? So more incrementally, more and more complex chemical molecules are going to be found at denser and denser regions. So not only CO, in the future you will find, I don't know, alcohol and stuff that actually makes life as we're doing right now, right? So yeah.
Let's give another round of applause to Dr. Hope Chen.